Hey y'all, it's Andrew Couch here, and in this Tidy Tuesday video, we're not going to be going over this week's dataset. Instead, I was looking over the Tidyverse blog and saw that there were a few updates on the TidyModels package, and I thought it'd be fun to kind of just investigate what they were doing in their changes and see how it can apply to our usual workflow. So one of the main changes that they made were the parallel processing with Tune and the sparse data structures in TidyModels. So with the sparse data structures and TidyModels, essentially they're going to offer different data structures that'll basically optimize the way our models will fit. And what this really means is ideally it should be fitting faster since it can handle like sparse matrices instead of your traditional data frames. So I was looking over what Julia Silges was doing, and she showed me her example. And I thought it'd be interesting to do to basically apply it to my own data set and see if it actually works, and maybe kind of analyze what's going on. And then they actually made a change to the the tune package, which basically enables parallel processing. So if you have worked with TidyModels and also worked with parallel processing, you'd basically know that using parallel processing comes with a ton of headaches. For me, whenever I would do some parallel processing, it would basically not allow me to do anything else after I finished the tuning. So how I would basically do it was I would create a separate script purely for tuning with the tuning grid, and then apply the parallel processing, export that model, and put it back into my analysis. But what they essentially did was allowed for different ways to parallelize your tuning. So one of the problems was basically working with resamples, so with your k-folds cross-validation dataset, and also your recipes. And that caused a lot of issues, but apparently they fixed that. So I think that'd be kind of cool to show you how parallel processing really works and how much better it is when you're using it for your own training times. Um, in general, basically, you just have to enable parallel processing. There's two options. Basically, using the everything and then resamples. So with parallel over resamples, it would essentially just apply the pre-processing once and then go through the resamples and fitting in parallel. With everything, it would do both the resampling and also the pre-processing. So I thought that'd be kind of cool to do an example and kind of show you what I found in my own data sets. I'm not actually going to type all this code out. I have already typed it in, and there's not a lot of code anyways. So I figured that it'd be better just kind of read over my notebook or my little R Markdown document and see what I did. So I basically loaded in the Tidyverse, TidyModels, TidyText, some text recipes, and Themis. These are all just kind of like text and machine learning packages, and also class balancing stuff. So I read in my Harry Potter text CSV. I essentially summarized it by each character, and then I basically combined all of the characters' text into one single value, and then I rebalanced the entire data set so it would be balanced towards the house, because we know from previous previous things that we have some imbalanced data sets. So I just did that where we have our house rebalanced so it would be equal for everything, just for sanity, and so it'd be a little bit faster. Usually I would just do it by a defined length of text, but for this example, I figured it'd be kind of easier to run all these models at once um, to assess the training times. So I did that where I basically rebalanced the data set. I set my seed, created my generic train and test splits, made a k-folds data, and then I actually went into what Julia Silly was doing and highlighting the first thing, which was the where was it? Which was the sparse data structures with TidyModels. So when I actually was doing some NLP work, I guess a year right out a year ago, I was basically doing it as like kind of like a naive way, how she was doing it, where essentially I was counting, I was computing my dictionary of words I wanted to use using the TF-IDF algorithm, and then basically using that as a dictionary, filtering it out. So then I could basically count out how many words each character was saying uh, for each sample. So for this, I'm essentially just creating a matrix, but I actually didn't convert it to a matrix. Instead, I just used it as essentially a traditional data frame where each column represented a certain word that was in my TF-IDF algorithm. So as you can see, these words seem to make a decent amount of sense. Most of them are names, which may cause probably some data leakage, because if someone's saying like Draco, they're probably like either like Gryffindor or Slytherin, etc. But for this example, I didn't like remove any names like I did in my original project. So I basically created a document term matrix, but I didn't convert it to anything. So you see it's pretty sparse. There's a bunch of zeros, and then there's occasionally a few eights and ones, etc. So I did that. I created my k-folds data set with this like naive matrix. And then I went on to do your generic pre-processing, what you really should be doing, where we're basically just doing some tokenization, removing our stop words, creating a token filter. So we're saying like max tokens is 75, and then we're computing the TF-IDF score. I also wanted to highlight some ways you can actually speed up your model training times is to kind of look at where your pre-processing is at and trying to remove expensive pre-processing. So I added step isomap, which is essentially like a clustering algorithm, I think, where it'll basically kind of combine these predictors into a few terms. This is pretty expensive, but honestly, both isomap and also like the tokenization part is pretty expensive, where we're basically trying to do all these counts every time. It's very expensive computationally compared to this method, where I'm essentially pre-calculating all of the bag of words and tokens, and then I'm just saying split it up into a data set, don't do anything else, and just train the model and run. So what I would expect is actually this to be slightly faster, but and realistically, if you want to do other pre-processing that's a little bit more complicated, so if you want to do more stop word removal, more token filtering, maybe you want to do like a topic modeling and stuff like that, or use embeddings, it might be easier just visually to see this. And when you're actually doing a model in production and you want some type of like stored feature list, this way was probably the better way to do it. So one of my next tips, which is pretty most people would know what to do for this, but when you're trying out models, definitely try a simpler model. So in this case, I actually choose a elastic net model, which is like a combination of a ridge and lasso regression, where I can penalize terms to be 0, but also I can just shrink them so it'll be approaching 0, not actually fully eliminate them. One thing I would also say is using a complex model like XGBoost is actually pretty terrible for a lot of NLP problems, especially multi-class NLP problems, because XGBoost just does not really work great with multi-class classification, at least in my own work that I've done. So that's just an example of a very complex model where if I was going to start out modeling a NLP project, I would definitely not start with XGBoost. I would definitely probably stick with an elastic model or even a k-nearest neighbor model. So I also want to show you some more efficient ways that try out different parameters. So generally, I will always use grid regular, but there's also grid max entropy, which will basically use different combinations of parameters in a more efficient manner. So if I actually compare the elastic grid and the elastic entropy grid, we can see that for the elastic grid, it's doing it more in sequential order, right? It's saying like, yeah, we want a penalty of 0.1, etc. And it goes up with all the combinations of mixture. Whereas elastic entropy is kind of just doing kind of the middle ground, where it's basically using a diverse pairing of parameters that aren't in the sequential order. So it's covering more distance with less sets of parameters, which will generally just show you if you're not sure how much you should penalize and stuff like that, you could get better results or at least faster training times using a different grid. Additionally, I've already gone over this too in some past videos, but just applying some actual filterings to your grids will make more sense, even though TidyModels will give you a pretty good default list of parameters. They will give you some weird ones where if I have an XGBoost model and I basically know that I won't only need one tree. It seems pretty pointless to include just one tree. I would probably use a decent amount of trees. Same with tree depth. I wouldn't expect, me only using one decision tree with one with a depth of one, right? Because that's just a generic decision tree. So I could filter that out and it'll kind of remove some of that garbage. Then we can compare the XGBoost grid with the XGBoost entropy grid. And we can see that for the trees, it's doing essentially 1, 1000, 2000, 1, 8, 15. Whereas the entropy or max entropy is showing a more diverse list of trees with a more diverse list of tree depths. So in this case, it's using a lot of trees, right? But it's also using a pretty deep depth for the trees. And sometimes I'll use less trees, but with a shorter depth. Whereas this one is kind of doing a middle ground of all of it, where I think like say 1008 and then 2008 and 8 might not be a great informative parameter set to use because they might be basically the same thing. Okay. So we can see how I guess entropy grid can do pretty well with doing more efficient, especially if you're maybe at a time crunch where we want a model out there for a meeting. We want to assess the results, but we also want it to be as accurate as possible. So instead of doing grid regular, you might do grid max entropy, so you can kind of get a better baseline of what you're trying to assess. Okay, and now I actually created I started tuning the models. So one of the ways to actually apply this different data frame type, or basically create a matrix instead of a traditional tibble, is you basically use hardhat and then you say default recipe blueprint composition equals DGC matrix. I'm sure there's gonna be more compositions or more data types in the future, but in the example they just use a document matrix. I basically assign that into the recipe. I'm basically saying like I want you to tokenize all these words, and then I want you to convert it to a matrix. Then basically tune the models, and I tuned the models and collected the results. So I created a beginning time, tuned it, and then I record the end time. And then I'm gonna put them basically together into a single table, and we'll see it at the end of the analysis. So I also want to do more. I want to show the more expensive preprocessing. So basically, just add in the expensive preprocessing recipe, same sparse document term matrix, tune it, collect the results, and we can see it's basically calculating all these things, creating the I guess clustering or embedding, and it's doing that multiple times for each resample. So you can see how that's a lot of work, and we could probably expect that it'll probably take a little bit longer to train than our other baseline recipe model. And then finally, I also showed a different way to tune your model, where essentially you don't give it a grid. Instead, you use a Bayesian approach. So with tune Bayes, what's kind of cool about it is you don't give it a actual grid, a parameter grid. Instead, you kind of just let it run, and it'll basically try to optimize a metric. It'll first give you one set of parameters, train it, then it'll create another set of parameters that'll be different. Basically have an expectation of it improving. So if the model doesn't improve with the resamples, it'll basically stop training. And you can actually set that threshold. So if on one hand, if you want to be a little bit more cautious about it, you might set the number of improvements to a higher number. So you want to make sure you're not just at a local minimum and you're actually at the global minimum or global maximum for depending, I guess, how you would refer to that metric. So you can do a decent amount of fine tuning for how long you want it to run. And I think there are some defaults to it with like the number of iterations or number of parameters it'll check. I think it might be 30, but you can definitely change that if you're using like a smaller model, like a lasso model where you essentially have one parameter. But it's always something to keep in mind. I think one good use case with a Bayesian approach is if you're, say, at home, you're going to go to bed, you don't really know what parameters you want to choose, but you want to tune it. And it doesn't really matter when it finishes as long as you have to give it a decent amount of time. So you could run like a tune Bayes instead of your generic tune grid and let it run overnight. You wake up and you have a fully tuned model with some results of like what your Bayesian approach was doing. You can kind of see the actual route it was taking or the number of iterations it took with the improvements of what score you're trying to optimize. And you can also specify what metric you want to optimize. So I ran that. It basically said that if it doesn't improve after 3 iterations or 3 pairings, you can stop. So we can see it running. We saw that there wasn't really any change. We see that it's like 0.883, 879, 879. So basically stopped. It says no improvements after 3 iterations, returning the current results. And we can see the different parameter sets it was trying. So its first parameter set was 0.000256. So not a huge penalty. You can see it doing a different one. You can see it doing another different one. So you can see it's kind of interesting how it's just choosing its parameters. I'm not sure if it's I think it might be a Gaussian process because it says Gaussian, but I wonder if there's an option to choose like some different type of process. So you could say like, I want to try this set of parameters, start at the bottom, start at the top of the list, go down and see how much it improves, etc. I think that would be an interesting implementation in this function. But I'm not sure really how the underlying functions work in TuneBase, but it'd be interesting to see what they start building upon it. And then lastly, I want to show you probably the thing that is used the most is the do parallel. I use do parallel. Sometimes I'll use future map, which is like the map where you can do parallel processing using mapping functions. I think that future map uses the do future or the future package. But when I do modeling, I just have always done do parallel just because there's more documentation on it, at least for a modeling standpoint. But I do like using the future and future map package. So I actually did this. It's the same thing. Adding actually parallel processing to your training process is very easy. Again, you just give it a model control or a control grid. So if it's a tune grid, it'd be control grid. If it's fit resamples, I think it's like control resamples. But they're the same thing. They have the same options. They're just for different functions, and they all correspond with each other. So the first thing that I added was allow parallel. So I wanted to allow parallel equals true. And then you have another option that they just added, which you can do either everything or resamples. In this case, since I was thinking that we're always going to be using the recipe package to basically tokenize each resample, I figured we want to basically parallelize the both the resampling and the preprocessing. However, if you don't really need to do that preprocessing of like tokenization, and maybe it's just like a generic center and scale or something like that, you might not even need to use everything. In that case, you'd probably do resamples. If you don't know, I believe you can just leave it blank. I'll basically decide for you. Oh, I also forgot that to actually register your parallel processing on your workspace, you just do parallel make psoc cluster. I said 4 because I have 4 physical cores on my computer, and then you register your parallel workers. You're also supposed to like stop the process, but in this case, I'm just not going to do it right now. But I think it's like a stop implicit cluster. Yeah, so it'd be stop implicit cluster, and then you would stop that parallel processing. And then finally, I actually just plotted out the train times just so we can evaluate, what were the actual results, and then we can kind of see. Then I can kind of explain what was actually going on. As you can see with Bayes, the Bayes tuning definitely lasted the longest, but this is highly tunable. So I could just set it for was like 2 iterations. It'd probably be a little bit faster. But with Tune Bayes, it's so much faster to just like start training than to actually determine your parameter grids, and it's highly customizable. Whereas with Tune Grid, if you already passed your global minimum or your global maximum for your parameters, it'll still keep going through the entire parameter set, and that can be pretty annoying. So it has its trade-offs, but I think Tune Bayes is definitely still a thing that you should kind of keep in mind when you're training up your models. As for our second longest training time, we can see that our expensive one took the second longest. But what's odd about this is compared to the traditional route where you use the recipe or use the document term matrix, they're actually very similar. So the expensive one is slightly faster, but not at a point where I would say it's not worth doing. And then with the naive is actually faster than basically all of the rest of the models. And I think the main reason why it's faster is because I pre-computed the TF-IDF score. So essentially, this isn't necessarily a fair comparison, but I just thought it was interesting, especially since Julius Lilly did show the example of doing the TF-IDF pre-processing and pre-computing it. So I would have expected the naive way to do it, where you just create the counts already and then you assess it later, to be a little bit slower. But maybe I'm doing something wrong. It's always something to consider where maybe sometimes the naive route will be easier and a little bit faster. With that being said, we can see that the parallel processing still beat the naive way to do it. So even with parallel processing and doing all that computationally expensive pre-processing with the recounting of the TF-IDF score, we can beat this naive not naive forecast, this naive processing where we already pre-computed it. So this kind of shows just how fast parallel processing is, which makes sense because parallel processing, you're essentially using like 4 times the computing power when doing it. But we can see here how even when we have these like pre-configured word counts, parallel processing will still beat it most of the time. So I know this is a pretty quick video. I wanted to make this video because I thought it was pretty interesting and I just saw it today. So I wanted to create a quick video about just how to speed up your model training time. Definitely something that's pretty interesting, and I'm pretty stoked to see what's coming up next with the tidy models. So with that being said, I'll see you guys next week and tidy on.